So most of y'all that are using this gauge, you know that you can change, and Bob said that it's set at 300 seconds at 18 milliamps. But if you want to minimize that gap, that sleep, you just set it the way you want it. You bring it down so that that span isn't at 18 milliamps and 300 seconds. So you can get rid of that almost. But then, like Bob said, you're going to use up memory. And why use it if it's not really recording any useful data for you?
There's a question, might as well answer this now, but someone asked, before you start the job, if the job will start after like 8 to 9 hours later, do we need to depassivate the battery or wait until start job time to depassivate? Is it harmful for the battery? 8 to 9 hours is not a very long time, so you can definitely depassivate it several hours before you start the job. It won't be harmful. The depassivation should stay in effect for 8 to 9 hours, probably 24, probably 48 hours, maybe even a week, I would say. However, I do recommend that you depassivate as close as possible till start time. But 8 to 9 hours is not a very long time, so that's plenty of time to have a good depassivation. Another question, is the data only retrieved once the tool is at the surface? Yes. The battery has to come back to the surface, then you hook it up to your to your interface box, and you download the data once you're connected to a computer. That's the normal way of doing it. There are ways to, and we'd have to work with you on that. The battery can communicate real time through your tool to the surface. So it can communicate all the data that you're collecting through real-time communication. But this is something that would have to be set up with your tool and the battery beforehand. But it does have that capability of doing it, and we can work with you on that. Trip.
So as Bob said, the data needs to reflect the downhole conditions, and it does, and it helps mirror what you're seeing on your tools. A lot of folks say, well, why do I need a gauge in there if I have these readings coming from the tool? Well, it's, I'm skipping way down there to the end of this, but it's third-party verification. Not all the time is your client's going to trust everything that your tool's recording, but when you have a mirror image of what went on downhole, that gives more credibility to your data and of course to ours. Then we also have the files or the information where we had this gauge tested in and out. I mean, we spent a great deal of time and money to ensure that our recordings are accurate. As far as I know, we're the only ones in the industry that went this far. We need this data to troubleshoot the battery. If you want us to be able to look at it and give you a determination what happened, we need some forensic information. Yeah, you can look at a battery, but a lot of times a battery is a battery. I mean, it doesn't unless it's vented or something, then it's vented. But a lot of times when we look at that data, we can determine so many things from our data. The accurate battery usage, of course, it's the current. You want to know that's probably the most important thing everyone goes for, unless there's a problem. They only want to get the current, not the current, but the usage, the amp hours used. And but when there's a problem, they want to dump everything and they want to look at it. So again, third-party verification is so huge for forensics and for you to show the credibility of your information and ours.
So as Trip mentioned, we did a lot of work to characterize the gauge. In other words, we tested against known values to see how accurate it is. So there's several slides here I want to go through just to show you briefly how we did that. We also can send you white papers on this that shows the complete data set. If you want to get this, just request it, send us an email, and we can send it to you. Anyway, this slide shows both as measurement accuracy versus temperature. So I figure it's about an error about 1% over the temperature range from 25 to 165 C. So we feel it's a very accurate voltage measurement. Next slide, please. And this shows how the temperature measurement varies with temperature. So it actually gets better as the temperature goes up, but you can see how we're within a few percent as the temperature varies. Next slide, please. And probably one of the most important features is the current measurement. So we feel it's very accurate. This shows how a constant current will be very accurate over time. So this shows the deviation over 5 hours with a 2 amp constant discharge. Next slide. And then pulsing is a bit more difficult to get. But this shows how we did a 2 amp discharge with a 24-hour delay, and it shows how the accuracy remained throughout the 24 hours. Next slide, please. And this is using a pulse, so 1 second, 1 amp pulse for 10 amp hours. Next slide, please. I know we're going through this quick. Like I said, we can send this to you so you can study it in more detail. But this is showing a very short pulse, like 25 millisecond pulse, and how we're able to measure that type of pulse. So we're sensing 1,000 samples a second. So we're very, it's very accurate. It'll detect very, very close, short pulses. Next slide, please. And then we took the gauge to a shock and vibration lab, put it on a slip table, like shown here, and, shaped it up, vibrated it, and, measured the gauge while it was being, vibrated and shocked. Next slide, please. And this next slide shows the test fixture that we set up the gauge inside. Had different accelerometers on it, including the control accelerometer. Next slide, please. And these next several slides show different ways of testing the shock, vibration, and there's several more on the white paper that I'm not going to show you here because there's so many of them. But this shows what it measures over, 1G sine sweep. Next slide. Then a 5G sine sweep, you can see where it's just over 5 Gs in the measurements. Next slide, please. And then a classic shock, 20G peak. We did several different ones, 5, 10, 20, 50 G. That's all in the paper. So we can share that with you. And then here's a vibration, 20G, 25G RMS over 5 minutes, showing how this is the actual data from the gauge that you're seeing here. Next slide. And then rotation, we ramped it up to 1,000 RPM. I'm sorry, 300 RPM, and then back down to 0 RPM in different steps over 15-minute period. And then next slide, please. This is probably most important, is showing actual MWD tool data compared against our gauge. So I think it was a Toltec tool that detected this measurement, and then we compared it to the gauge. So you can see the RPM within 2 RPM, shock very, very close, vibration as well, very close. It probably won't be exactly the same because they're in different locations of the tool, but I would say this is pretty close. Next slide, please. We have a few case studies here. I'll just want to show you what the gauge can do for you if there's a problem. So we've had this happen a few times where a customer has reported that capacity used was much higher than expected after the tool sat for 3 weeks sitting on the surface. Little did they know that the battery was actually discharging. They thought, well, we put it on the surface, it's not discharging. But the Criterion data, which is shown on the next slide, please, will show that, well, hey, the battery was actually discharging over the entire time it was sitting on the shelf. So, a 3 weeks period, it actually discharged the battery to depletion without them knowing it. So this helped them understand, well, shoot, if it's sitting on the surface, it may be discharging. Maybe we have to somehow turn off the battery to keep it from discharging. So this has helped several times the customer to understand what's going on. Next slide, please. So in this case, the customer had some transorb damage in his tool. It resulted in a high current draw that caused damage to the cells. So we were able to look at the EBL files. By the way, in every case here, it was us working with the customer to help them understand what they were seeing with the EBL. So if you're ever using this, if you're ever using the gauge and you have a question, send us the EBL and we can look at it and help you understand what you're looking at. We'd like to give you that service. So if you ever have a question, we can help you with that. So anyways, next slide shows the where a very, very high current pulse occurred, and then the current dropped fairly low afterwards. And it showed that even though the fuse was not open in the battery, the high current caused internal cell damage. Basically, there's a secondary feature in some of the cells that will disconnect inside the cell, pretty much acting as a fuse. And if you go to the next slide, when we zoom in, you can see where the peak current was holding over 6 amps for several seconds. And that caused the internal anode tab in the cell to melt and disconnect and basically stop the battery from discharging. But 6.8 amps is quite a bit of current. And the gauge is actually limited to 6.8 amps. So the current was probably much, much higher in this particular case. But this showed the customer, hey, this is a problem. This is not normal operation. So they had to look in to see why this was happening. Next slide, please. So here's a case where the battery had both batteries in the tool string had blown fuses, and the batteries were very dirty, as you can see here, due to aluminum dust. And the next slide will show incredibly high vibration and shock, 195, 162 Gs of shock, vibration over 30 Gs of shock. So they were able to use this data to go back and say, well, this is a very, very rough period of use. So this caused damage to the tool, which probably caused short circuit currents and caused those fuses to blow. Next slide, please. And this is another case where a battery short circuited due to a lot of vibration and shock. And you can see here, there's a high current pulse highlighted there over 6.7 amps, which is, as you said, is pretty much railed to the max. So it's probably likely much higher. So then the fuse blew. And after that, the current was very, very low. And, this gave them an indication why they had a problem with some sort of current issue. Next slide, please. And then, anyway, the EBL file confirmed there were very rough conditions and it correlated with the customer tool data. And actually, I'm sorry, I forgot this was here, but if you can back up 2 slides, please. I just want to point out the rotation, the purple thing showed 81 RPM, 81 RPM. So you go back forward 2 slides. This is showing this is showing the rotation being very high as well as shock and vibration. So we were able to correlate the tool data, or excuse me, the EBL file to the tool data using this information. And this again, I think I got out of order there, but this shows the rotation being 180 RPM, which correlated with the rotation data on the previous slide. And this also is from that same thing, showing the shock histogram. You can see there was a lot of shock way up there towards 200 Gs. So this helped them understand, and actually, as you know, Chip pointed out, it gives the customer third-party verification to what they're seeing with their tool data. So before we go into this, there was a question on sleep-wake states. How much current will the gauge consume during sleep mode to avoid battery building passivation layer? Well, actually, the gauge does not consume a lot of current while it's in sleep. I can share this screen showing you the different sleep states that the gauge will do. So there's 3 different sleep states. When we ship it to you, it's shipped to you in deep sleep, which basically will draw about 200 microamps. Once you enable logging after you receive the battery, and then it goes to sleep, it's going to go into regular sleep, which is 1 milliamp of current. When you're actively discharging and the gauge is actively recording, it's going to draw about 5 milliamps in addition to whatever your tool is drawing. So this box over here shows how long the battery will last in different sleep states. So 16 years with the deep sleep, 3.5 years with sleep. In a typical 300-hour run, the gauge will use about 5% capacity. So really the question was asking, will the sleep states avoid the battery building a passivation layer? The answer is not really. It's not enough current to do that type of thing. So don't use the sleep state to keep the battery from passivating while it's in sleep mode. You'll still probably have to depassivate it before you actually use the battery. So I'll go back to the presentation, please. So just briefly, we did mention we wanted to talk about shipping to MENA countries. We have been very successful in shipping lithium batteries, which are dangerous goods, to pretty much all the MENA countries. We've never been unable to ship to these countries. They're not always easy. There are some hurdles. For instance, Saudi Arabia requires a safety test to register for the SABRE certificate. We have actually tested most of the most of the standard MWD batteries for import to Saudi Arabia. So we should be able to do that for you. If it's a battery that we have not tested, we can easily do that for you. But we also have worked with a variety of freight forwarders and shipping companies to get the batteries into MENA. So it's really not a problem. I think we can do it. May not happen overnight, but we can get into most countries successfully. And lastly, we're not going to go into safety handling here because that's a whole thing in itself. We've done it in the past, but we do have videos online on our YouTube channel. If you can scan this QR code, we'll leave it up here for a minute. It'll take you to the YouTube channel safety and handling videos, and we will include that in our follow-up email so you can find it later.